Friends, welcome to this class. So in this video we are going to discuss the stereochemistry of nitrogen, right? So in last video we saw the basics, right? So for example, coming to the nitrogen, so we know we have studied about CH4, NH3 and H2O. All are sp3 hybridized, sp3, right? So if you see its geometry, all are tetrahedral. But if you see shape, SHAPE shape, this is geometry, all are tetrahedral only. Shape, this CH4 is tetrahedral, this NH3 is pyramidal, and this H2O is bent shape or V shape we call. Why this is so? Because carbon, hydrogen like this, so structure will be like this, CH4. For NH3 there will be lone pair, right? So it will be like this, NH3. For water there will be two lone pairs, right? So shape we will see only this bonded, no lone pair, total shape. So it looks like pyramidal, right? So it looks like V shape or the bend shape, whereas this is tetrahedral. So geometry for all are tetrahedral, but shape will be different. These things you know, right? And we know that this CH4 is optically inactive, right? Because all are carbon. If I have carbon to which A, B, C and D, all different atoms are attached to this carbon. This is E, let us see, because CC, right? So all different atoms are attached to the same carbon. This carbon we call it as chiral and it is optically active. So let us see with nitrogen. So nitrogen, here we have lone pair, so that is different. Here I have A, B and C, and we expect this nitrogen should be optically active. But with some molecules it is optically active, with some molecules it is optically inactive. You will ask why it is so, sir, right? So reason I will explain it. So this is nothing but the stereochemistry of nitrogen, right? So we will see the stereochemistry, why it is optically active, why it is not optically active. That thing we are going to see in this video. So with respect to nitrogen, what we have, let me take it is R1, R2, and R3 and R3, R2 and this is R1. And here I have lone pair. So all different atoms are attached to nitrogen. So if you see the for this, if you see the bond angle R1 nitrogen R2, it will be around 107 degree. And also if you see dipole moment, it will be having some dipole moment, right? Right? So it will be like this. Yeah, based on R we can tell dipole moment, and also right bond angle will from that it is clear that it is not planar, right? But you will tell, since all different atoms are attached, there is no center of symmetry, plane of symmetry, axis of symmetry, mirror plane of symmetry, no those things are there, then it should be optically active. Why it is optically inactive, right? Why it is optically inactive? Because all these are absent in this molecule. It should be optically active, but I am telling it is optically inactive. Why it is so? The reason is, in our room temperature the energy will be around 20 kilocalorie per mole, right? Let me check it, because I should not give you wrong data. It is 20 kilocalorie per mole. I guess it is the same. Where I have written it, I have written it somewhere. I am not getting it here, right? Let me check it. Yeah, room temperature. Sorry, I am not getting it here. Where I have written, I have so many notes, I am not getting here, right? So just you think, in room temperature it is 20 kilocalorie per mole, right? And for this compound, the nitrogen attached to all different atoms R1, R2, R3, and here we have lone pair. With this energy, this This carbon is sp3, right? sp3, and these lone pairs present in sp3 hybridized orbital. It will convert into planar structure like this, in which nitrogen R1, R2, R3 all are in same plane like this. Within this plane all will be there, and there will be p orbital in which the lone pairs will be present, right? So there is p orbital. So if you see here the nitrogen hybridization, initially it was sp3, but here it will be sp2. It means all are in single plane. These lone pairs are present pure p orbital, right? Further what happens with this room temperature, for this much of energy, again there is inversion, right? So it will be like this. So here see this molecule, nitrogen is here, above lone pairs are there, R1, R2, R3 like this it is. Further what happens, at this energy it converted like this, planar, in which R1, R2, R3 and nitrogen all are in single plane, and there are pure p orbitals in which lone pairs are present. So the nitrogen hybridization is sp2, right? Further what happens, initially it was like this, now it became like this, now it will become like this. All these will go above and this lone pairs comes below like this. So it will become like this, all will go above, R1, R2, R3, and this lone pairs comes below. This mechanism we call it as pyramidal inversion. This can be called as pyramidal inversion or oscillation. So these molecules, the nitrogen containing other atoms molecules are there, right? Those are called rotomers. Why these are called as rotomers? Because see, we expect all different things are there, R1, R2, R3, different atoms and lone pair, right? So it is optically active, but it is not optically active because in one of its transition state, this we call it as transition state. In one of its transition state, it will be having planar structure because of sp2 hybridization. It will be having planar. Since it is planar, nitrogen and all R1, R2, R3 are planar, it is having plane of symmetry, right? So a plane can cut the molecule because we won't see this lone pair to tell the symmetry, right? So because electron density here equally distributed, so we won't discuss. So R1, R2, R3 and nitrogen all are equally halved, so it has got plane of symmetry, so it will be optically inactive. But we can stop this pyramidal inversion. How that everything we shall discuss later. So this pyramidal inversion, the energy required for pyramidal inversion is just 6 kilocalorie per mole, right? But in room temperature we have 20 kilocalorie per mole. So energy is sufficient for this inversion, right? So it can easily convert from like this, it will get inverted or oscillated or rotated from above, it becomes below through a planar transition state. That is nothing but this thing, in which nitrogen hybridization is sp2. Here sp3, there sp3, here pyramidal shape, but at the transition state it is planar. So there is plane of symmetry, so it is optically inactive. So this kind of inversion we call it as pyramidal inversion or oscillation, and energy required for that inversion is just 6 kilocalorie per mole, or at 6 kilocalorie per mole. So room temperature more energy, so more inversion, so such compounds are optically inactive. I hope you got it, right? I hope you got it. Yes, yeah, the data is correct because I got the thing here, the data is correct. So you will ask, sir, how to stop this pyramidal inversion? Yeah, there are things to stop the pyramidal inversion. The thing is what? See, so if I take this NH3 molecule, NH3, so it will become planar, and this electrons will in pure p orbital, whereas this hybridization is sp2 and it is planar. whereas it is sp3 and it will be pyramidal, and further again like this it will happen, and here we'll get lone pairs here like this, right? So this is pyramidal and again sp3, right? So this is the thing, this we call it as pyramidal inversion, right? So how to stop it? So see, if I could increase the energy of the molecule more than this 20 kilocalorie per mole, which is the energy of room temperature, then there is no inversion, right? So for to do that, what I will do, see, I will take this nitrogen, I will make a ring like structure. So it is a 3-membered ring. Here I have methyl and here I have one more methyl, and here lone pair. So this nitrogen atom attached to 4 different atoms. So this is A, I can call this is B, this is C, and this is D, lone pairs, right? So we expect it should be optically active because 4 different atoms. So we expect optically active. Yes, this is optically active. Why it is optically active? Because the energy of this molecule they haven't written, but it will be more than 50 kilocalorie per mole, right? So room temperature it is just 20 kilocalorie per mole. Since the energy of this molecule is more than say 50 kilocalorie per mole, so this molecule doesn't undergo any inversion like this. So no pyramidal inversion. So that compound is optically active like this, right? So this is the method, right? And also it is seen that the energy of this molecule compared to the energy of this molecule, all 3 hydrogen replaced by deuterium D, the energy if you see, it will increase here, from here to here it will increase, right? So as soon as it increases, so what happens, the rate of inversion becomes decreases. So in exams they will ask you, they will give these 2 molecules, and if you want to arrange in the rate of inversion, you will tell it that this NH3 it will do more inversion, fast inversion compared to ND3. Why? Because as atomic mass of this D increases, the rate of inversion decreases, right? So rate of inversion, so here the rate of inversion will be more and rate of inversion will be less. So this is the order for rate of inversion, please note it, which because I have not written it, right? So this is the thing, right? So once we study all these things, now we have to give the energy diagram for it, right? Because energy diagram, how to give it, let me tell you, right? Energy diagram, so it can be given it like this. So here it is sp3, so here energy like this, and here reaction coordination like this. So here the nitrogen shape is like this, NH, H, H and lone pair. Energy is this much, 6 kilocalorie. Afterwards what happens? With room temperature it will convert like this, ion it will convert like this. This is our transition state in which all these hydrogens are in same plane, and hybridization of nitrogen is sp2, here hybridization is sp3, right? And all are in same plane, and these lone pairs are present in pure p orbital, and here we have nitrogen like this, lone pairs here, 1 hydrogen, 2 hydrogen and 3 hydrogen. So here it has been inverted. During inversion, through a transition state, which I have written it here, this is the energy diagram. So like this, it converted to like this through a transition state, and this is the energy diagram, right? So this is the thing, I hope you got it, right? So this is the energy diagram for this nitrogen inversion. And also I told, to stop nitrogen inversion, we can make a ring, 3-member ring. If we do, the energy of the molecule increases more than the room temperature, so the rate of inversion decreases, so we can isolate that molecule in pure state, that is optical activity we can check for that molecule. So that is the thing. Once we saw all these things, let me tell few more things, right? So you will ask now, sir, we believe pyramidal inversion is happening everything, we want the we want the proof for this. So Proof for this pyramidal inversion, we can give it through proton NMR. 1H NMR. What is this proton NMR? So they took this compound. So here nitrogen was there. They took this compound. Here above one hydrogen, below one hydrogen, above one hydrogen, below one hydrogen. It was like this. Right. Here I had ethyl, and above we had lone pairs, like this. So if you see, at room temperature, they took the proton NMR. They saw that these protons, these two protons and these two protons, all are equivalent, right? We know the HA, these are equivalent, and at room temperature they found that these hydrogens were equivalent. But at lower temperature, very lower temperature means less than 0 degree Celsius. I don't know. Yeah, they carried out the reaction at minus 50 degree Celsius. This much lower. At lower temperature, they found out that, see, this is below, right? This is below ethyl. This lone pair is above. Here this hydrogen is above. This hydrogen is below. So below ethyl I have, below this hydrogen I have. Whereas this hydrogen is above. So there will be some interaction between below and above, because here I have bulky ethyl. So repulsion will be there with this below hydrogen. So at lower temperature they saw that these two hydrogens were different. Initially at room temperature those were equivalent, but at less temperature, at minus 50 degree temperature, they saw that this HA, since it is above this with ethyl, so it is trans. HA was trans, and HB, let me call now it as HB, as it is below to this ethyl. With respect to ethyl, it is cis. Here also I saw this with respect to ethyl only. With respect to ethyl, it is below, whereas HA is above, so it is trans, and HB is below. This is also below, it is cis. They saw that for trans, the proton NMR ppm value was different, and for this HB, the ppm proton NMR value was different. So they could distinguish between HA and HB, but at very lower temperature, that is minus 50 degrees Celsius. So what they concluded, so at room temperature this compound is optically inactive. Why it is optically inactive? Optically inactive, and it will undergo this pyramidal inversion. Initially it will be like this, becomes like this, and below it will go. So like this it will happen at room temperature, but at lower temperature the pyramidal inversion will be restricted. So there is no pyramidal inversion, because of which we can distinguish between these protons HA and HP. So this is the proof, so that this whether nitrogen is undergoing pyramidal inversion or not, right? So I hope you understood it. So like this they studied all those compounds and they came up with the conclusion, right? So these basics you should know it, right? Energy diagram also I have given, so many things I have given. So they observed for few compounds. For example, they took nitrogen with lone pair. Here they took methyl. If simple line, you should know that it is methyl. Further what they took compound like ethyl, CH2, CH3, right? Ethyl. Further they took this compound nitrogen with isopropyl, right? And lastly they took this compound nitrogen with tertiary butyl, right? So these compounds they took A, B, C, D. So what they have done, from left to right, A to D, they have increased the steric hindrance. They have increased the steric hindrance. Now they are going to study the pyramidal inversion for this compound. Pyramidal inversion. So what they got is, see, pyramidal inversion of D was very much compared to C, then comes B, then comes A. That means this D was going to be inverted very fastly compared to this A, and the reason they told, because of steric hindrance, you know, all these have bond angle around 107 degree, right? So during pyramidal inversion, it comes to a transition state like this, right, in which the hybridization of this nitrogen is sp2. Since it is sp2 means bond angle will be 120 degree. So initially all are having 107 degree, but because of this steric hindered molecules, the repulsion will be more. Repulsion will be more means they easily come to planar structure like this. They comes into planarity. Compared to this methyl, the tertiary butyl will come very fastly, right? So that is the rate. So they all come to the planar structure because of this repulsion between two bulky atoms. So easily they come into planar structure, right? Initially they were like this, because of repulsion they came into planar, and also they will rotate like this. So inversion, rate of inversion for that D was very fast. Because of repulsion they came up into planar. So that is the order, right? I hope you understood. So they can come from 107 degree to 120 degree. Here it is more compared to this because of steric hindrance. So you should remember that whenever there is steric hindrance increases, the rate of pyramidal inversion also increases. So here you can see the D is more easily inverted. So if it is the rate of inversion, then what is the energy of inversion? Energy of inversion will be reverse of this, because see, for D it is like this, for C it is like this, for it is B it is like this, and for it is A, right? So this is the thing. So inversion is very more for D. See, D, C, B, A, D, C, B, A. So inversion is more. Here easily inversion, here little less, here little more less, and it is least. So this is the rate of inversion. So D is more than C, more than B and A. If you see the activation energy, so this is activation energy. So it will be reverse of the rate, because see, it is more easily inverted means activation energy will be very less. So order of this activation energy for D is very less compared to C, compared to B, and compared to A, because for A the activation energy is very high because inversion rate is very less. So both are opposite, in which the molecule will undergo very fast inversion, will be having low activation energy. Because of this energy only it will going very fast, right? That is how you should remember. So if we increase the steric hindrance, the inversion also increases. So to restrict it, what we can do, we can take a ring like this, cyclo like this. Within the ring we will hold that, so that the inversion will be decreased because of that 60 degree. See here the bond angle is 60 degree. Alright, let me explain it. I have got 7 more minutes. I have to explain it. So to stop the inversion, what we will do, we will take this nitrogen, and here I have methyl, let us assume, and lone pair, right? So to decrease the inversion, what we will do, we will make a ring like structure. If ring is there, if you see the bond angle, it is 60 degree. So in inversion it should come to a planar stage like this. It should be planar it should be. So here bond angle is 120 degree. So from 60 to 120 degree, the rate, see, if it comes to planar, the ring will break, right? So ring will break. So what it will do, it won't undergo any inversion, no pyramidal inversion. And if we want to see the energy of it, they have given here, they haven't taken methyl, they have taken phenyl. This is one molecule, they have taken this more molecule, SO2PH, and they have taken one more molecule, this one. Here chlorine is there and here methyl, and they have written the energy. For this it is 47 kilocalorie per mole. All are in kilocalorie per mole. It is 47 for this molecule. For this molecule it is 52, and for this molecule it is 100. Whereas room temperature it is 20 kilocalorie per mole. Right. So these compounds can be easily isolated. in pure form, right? Because they will not undergo pyramidal inversion. So here no pyramidal inversion, right? So this is the thing you should remember, no pyramidal inversion. Why no pyramidal inversion? Because if they undergo pyramidal inversion, initially they have bond angle 60 degree, they have to come to 120 degree planar structure. So 60 to 120 degree, there will be more, the ring will break only, so they won't undergo pyramidal inversion. So if we increase the ring size, from nitrogen it is 3 membered, 1, 2, 3 membered, right? If I convert it into 4 membered, the rate of inversion increases. If I convert it into 5 membered, again easily it can invert, so it can do pyramidal inversion. If I convert into 6 membered, then easily it will do pyramidal inversion. So in exams they may ask you like this also. They may give 3 membered, 4 membered, 5 membered and 6 membered, and they may ask you write the rate of pyramidal inversion. So pyramidal inversion in 6 membered will be more, then 5 membered, then 4 membered, lastly comes 3 membered. One thing. And also they may ask you to write the activation energy or energy required for inversion. The energy required for inversion of this 3 membered will be very high. So for A, this will be high, then this, and then this, like this. The reason is because it is less inverted, so more energy, like that, because both are inversely proportional. I hope I covered so many things. I have left few more things that I will cover in the next class. Till then, take care and have a great day.